This video is going to have a look at some giant covalent structures of carbon, and we call these allotropes. There's different forms of the same elements. They're allotropes of carbon. And when we talk about giant covalent structures, we talk about lattices and we talk about repeating patterns. And there are two ones that you really need to know. So the first one that you really need to know is this, and this is diamond. And diamonds you're probably all familiar with. They're the hardest natural material we come across. Their melting point is incredibly high, and the reason is they've got these strong covalent bonds, and each carbon has 4 covalent bonds. Now don't be fooled, because there are diagrams that are like this where they have carbons that only have 1 covalent bond. This is a repeating structure, so actually they do have 4 over here, but if we kept drawing them, the diagram would go on forever. So diamond only has 4 bonds to each carbon. Every carbon has got 4 covalent bonds, and these bonds are very strong. And it's a little bit like trying to tear a book, right? You could tear a single page, but because there's so many pages, if you tried to tear them all at once, which is what melting essentially is, trying to break all of these bonds at once, it takes a huge amount of energy. So as a result, they have a very high melting point. Now, because they're in this regular lattice, which is called a tetrahedral shape, it means that they are also incredibly hard. So diamond in itself is incredibly hard, and it doesn't tarnish. So we use it in things like jewelry. We put it on the end of drills to help drill quite difficult materials. So that's diamond. If we look at what's more common, which is graphite is what we use in pencils. And you'll notice there's a key difference here. Whereas the diamond is tetrahedral, this is planar, so this is flat. It's all on one dimension. Each carbon is connected to 3 different carbons. So there's 3 covalent bonds. So what's happening to the other covalent bond? Well, the other electron that would form the covalent bond is delocalized. So it floats between these layers, which means it can now conduct electricity. So if I put a current in here, the electron that's spare can float a little bit like in a metallic structure. It can move from one side to the other and carry a charge. This means, a little bit like a book again, the layers are actually quite strong, but the forces between the layers are quite weak. So you can just slide those pages over each other. You can slide the layers off of the graphite because the connection between them is a lot weaker than the connection within each sheet. The sheets themselves are called graphene, and this is kind of a new area of nanotechnology that's proving quite popular. And it means that you can have a thin surface that conducts electricity over the top. So it's used for things like circuit boards. However, their melting point is the same as diamond because they're essentially the same structure. There are lots of covalent bonds, a giant lattice structure where you have to break all those bonds at once. So the melting boiling point sort of, again, it's around 3,000 degrees. And then we look at this. This is called a nanotube, and this again is like a sheet of graphene. So it's got 3 covalent bonds to each carbon, and it's basically taken a sheet of graphene and rolling it into a tube. And it works because you can almost turn these into wires because you've got an electrical current that can go through because the 4th electron in each carbon is delocalized, just like in graphite here. And the individual sheets of graphene and on the graphite, which is lots of layers of graphene, the electrons are delocalized and can move. Similarly, the electrons are delocalized and can move up and down the tube. So this is a way of conducting electricity. It's similar to a wire, and it can be worked as a wire, but it's a lot stronger and more rigid. And then lastly, we come to something that isn't a giant structure, but another allotrope of carbon that you need to be aware of. And this is called Buckminster fullerene, or C60. And it's 60 carbon atoms. Now, again, if we take one of those nanotubes and cut it and then fold in the ends, that's what you essentially get with Buckminster fullerene. It's 3 covalent bonds. The 4th electron is floating around on the surface. It's got a much lower melting point because it's a simple covalent structure. It's just a big simple covalent structure. So it's actually the bonds that you're breaking between the Buckminster fullerenes that turn it into a liquid or a gas. So the melting point is much lower than in these giant covalent structures. We use this for like delivery of medicines because it's charged, you can stick medicines to the outside and it sort of stabilizes them.